Connecting the equipment grounding conductor or EG inside the meter is incorrect and potentially dangerous. The EGC must be connected to the meter box, not the meter itself. Connecting the EGC improperly can create a serious safety hazard, increasing the risk of electric shock or fire. The primary function of the EGC is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. This rapid clearing of the fault minimizes the duration of dangerous touch potentials. The correct procedure for connecting the EGC is as follows. Firstly, turn off the power to the meter at the main breaker. This ensures that you are working on a de-energized circuit, minimizing the risk of electrical shock. Secondly, remove the cover from the meter box. This provides access to the grounding terminals within the meter box. Thirdly, locate the EGC terminal on the meter box. This is typically a green screw or a terminal block specifically designated for grounding conductors. Fourthly, connect the EGC to the EGC terminal. Ensure the connection is mechanically sound and electrically continuous. Fifthly, tighten the screw or terminal block to secure the connection. A loose connection can lead to increased resistance and ineffective grounding. Sixthly, replace the cover on the meter box. This protects the internal components from environmental factors and accidental contact. Seventhly, turn the power back on at the main breaker. Verify that all circuits are functioning correctly after restoring power. Understanding the National Electrical Code or NEC requirements for grounding is crucial for electrical safety. Article 250.4 of the NEC covers general requirements for grounding and bonding. It emphasizes the need to create a low impedance ground fault current path and to minimize ground fault voltage. Section 250.24 outlines specific requirements for grounding service supplied alternating current systems. This section details how to properly connect the grounding electrode conductor and the equipment grounding conductor. The equipment grounding conductor serves to connect the non-current carrying metal parts of equipment, raceways, and other enclosures to the grounding electrode conductor or to the grounded conductor of the system. This connection ensures that these metal parts are at or near ground potential, minimizing the risk of electric shock if a fault occurs. Consider a scenario where a fault occurs within an electrical appliance. Without a properly connected EGC, the fault current might energize the metal enclosure of the appliance. If someone were to touch the energized enclosure, they could receive a dangerous electric shock. However, with a properly connected EGC, the fault current would flow through the EGC back to the source, causing the circuit breaker to trip and de-energize the circuit. This rapid interruption of the power supply prevents the metal enclosure from becoming dangerously energized, thus protecting individuals from electric shock. The NEC also specifies requirements for the size of the EGC. Table 250.122 provides guidance on selecting the appropriate size of the EGC based on the rating of the overcurrent protective device. It is important to consult this table to ensure that the EGC is adequately sized to handle the potential fault current. Using an undersized EGC can lead to overheating and potential failure of the grounding system. Bonding is another critical aspect of electrical safety. Bonding refers to the connection of metal parts to form an electrically conductive path that ensures electrical continuity and the capacity to conduct safely any fault current likely to be imposed. Section 250.92 of the NEC addresses bonding of services. It requires bonding all metal enclosures containing service conductors, including meter enclosures, to the grounded conductor. This bonding minimizes voltage differences between metal parts and provides a low impedance path for fault current. Proper grounding and bonding are essential for protecting electrical equipment and personnel from hazards associated with electrical faults. It is imperative to follow the NEC guidelines and best practices when installing and maintaining electrical systems. The grounding electrode system typically consists of a grounding electrode conductor, which connects the equipment grounding system and the grounded conductor to a grounding electrode. Common grounding electrodes include metal underground water pipes, metal frames of buildings, concrete encased electrodes also known as UV grounds, and ground rods or pipes. The selection of the appropriate grounding electrode depends on site conditions and the applicable requirements of the NEC. Ground rods, for example, must meet specific requirements for depth and spacing. Section 250.53g of the NEC requires that ground rods be driven to a depth of at least 8 feet and be spaced at least 6 feet apart. This ensures that the grounding electrode provides an effective path to ground. The resistance of the grounding electrode system is also an important consideration. Ideally, the grounding electrode system should have a low resistance to ground, typically 25 ohms or less, as specified in NEC section 250.53 A low resistance ensures that fault current can flow easily to ground, facilitating the operation of overcurrent protective devices. If the resistance of the grounding electrode system is too high, it may be necessary to install additional grounding electrodes or improve the existing electrodes. Regular inspections and testing of the grounding system are essential to ensure its effectiveness. Ground resistance testing can be performed using specialized equipment to measure the resistance of the grounding electrode system. These tests should be conducted periodically to identify any potential problems or deterioration of the grounding system. In addition to grounding, surge protection is another important aspect of electrical safety. Surge protective devices, or SPDs, are designed to protect electrical equipment from transient voltage surges, such as those caused by lightning strikes or switching operations. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. The NEC requires the use of SPD in certain applications, such as in dwelling units and at service entrances. The type and rating of the SPD should be selected based on the specific application and the expected surge environment. Proper installation of SPD is critical to their effectiveness. The SPD should be installed as close as possible to the equipment being protected and should be connected to a dedicated grounding electrode conductor. In summary, grounding is a fundamental aspect of electrical safety that protects both equipment and personnel from hazards associated with electrical faults. The equipment grounding conductor, or EG, plays a critical role in providing a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. It is imperative to follow the NEC guidelines and best practices when installing and maintaining electrical systems, including the proper connection of the EGC, the selection of appropriate grounding electrodes, and the use of surge protective devices. Remember, working with electricity can be dangerous, and it is always best to consult with a qualified electrician if you have any questions or concerns about electrical safety. Neglecting proper grounding practices can have severe consequences, including electrical shock, fire, and equipment damage. Always prioritize safety and follow the established codes and standards. When dealing with electrical systems, understanding the concept of impedance is crucial. Impedance, measured in ohms, is the total opposition that a circuit presents to alternating current. It includes both resistance and reactance. Resistance is the opposition to current flow due to the material itself, while reactance is the opposition to current flow due to inductance or capacitance. In grounding systems, a low impedance path is essential for effective fault current flow. This means minimizing both resistance and reactance in the grounding conductors and connections. High impedance can impede the flow of fault current, slowing down the response time of overcurrent protective devices and increasing the risk of electric shock. Several factors can contribute to high impedance in grounding systems, including loose connections, corroded conductors, and undersized grounding conductors. Regular inspections and maintenance are necessary to identify and address these issues. In addition to impedance, voltage drop is another important consideration in electrical systems. Voltage drop refers to the reduction in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can also increase the risk of overheating. The NEC specifies maximum allowable voltage drop for branch circuits and feeders. To minimize voltage drop, it is important to select conductors of adequate size and to keep circuit lengths as short as possible. Proper grounding and bonding practices also contribute to minimizing voltage drop. The grounded conductor, often referred to as the neutral conductor, plays a crucial role in carrying unbalanced current in three-phase systems and serving as a return path for single-phase loads. The grounded conductor must be properly sized and connected to the grounding electrode system to ensure that it functions correctly. Incorrectly sized or connected grounded conductors can lead to voltage imbalances and increased risk of neutral to ground voltage, which can cause equipment to malfunction or fail. When working with three-phase systems, it is important to understand the different types of configurations, such as Y and delta. In a Y-connected system, the neutral point is typically grounded, providing a stable reference point for voltage. In a delta-connected system, the neutral point may or may not be grounded, depending on the specific application. The choice of grounding configuration can affect the performance and safety of the electrical system. Regular maintenance of electrical systems is essential to ensure their continued safe and reliable operation. Maintenance activities should include visual inspections, testing of grounding systems, tightening of connections, and replacement of worn or damaged components. A well-maintained electrical system is less likely to experience faults or failures, reducing the risk of electrical hazards. Remember that electrical codes and standards are constantly evolving to reflect new technologies and best practices. It is important to stay up to date on the latest changes to the NEC and other applicable standards. Continuing education courses and professional development opportunities can help electricians and other electrical professionals stay informed and maintain their skills. Following the NEC guidelines and employing sound engineering practices are essential for creating safe and reliable electrical systems. Neglecting these principles can have serious consequences, including electrical shock, fire, equipment damage, and even loss of life. Always prioritize safety and seek the advice of qualified professionals when working with electricity.